Can you unshare, I guess, Marcus? Yeah, thank you. That's great.
Okay, now I share. Huh? Hi, hello.
Hi. So, Hendrik.
Okay, good.
From Southampton, and off you go.
Thanks a lot. Okay, I hope you can hear it and see me, or see the slides, rather.
Yes.
Okay, so thanks first of all to the organizers for having me, and also for this nice meeting. I tried to join as much as I could in the past days, and it was very inspiring. And I will basically talk about the stuff we do in Southampton, so levitated mechanics. So you will see there's a lot of overlap with what Marcus just talked about, so I will try to say some other things which Marcus maybe has not mentioned. I try to it's maybe the wrong decision. You will tell me afterwards, but I basically will try to talk about everything. So I will not structure it nicely. I will just go through the ideas which we have developed in the past and things we are working on, really more, to give you an information about what we are doing. And I'm happy to discuss basically all of the topics in more detail. If you have questions, the first slide is just to thank people involved in this, the project, and the experiments and theory. So I used to say that I'm an experimentalist, so I will talk mostly about the experiments, but when I look back, in the past 10 years, I would say at least half of my efforts in research in this fields have been actually more working on proposals and working with many different colleagues, theory colleagues, to actually work out what are the ideas which we can test with these systems. So the stuff I will talk about is the optical levitation, to use lasers to levitate nanoparticles, 100 nanometer particles. Then I will go through some of these proposals which we have put out in recent years, and then I talk about the more recent magnetic levitation experiments, where we use Meissner levitation. So we have actually a permanent magnet which we levitate above a type 1 superconductor. And then if time allows, so Peter has to stop me, I guess, at some point, I will talk about even more proposal ideas. And so I will try to focus on the short range effect, so because that's the topic of the session. But of course there are other things which are related. So the first slide is just an overview of some of the things which we have done experimentally with levitated optomechanics. If you can see my cursor, so we have basically a specific type of an optical trap. We use a parabolic mirror to focus the light and trap these silica nanoparticles there. And we used it to, look into force sensing. We did some state preparation in the classical sense. So a thermal state, which then was squashed, so it's not squeezing. We also had a Kalman filter applied to the system in a real-time Kalman filter to also do cooling. So in our case, it only went to some 100 microkelvin, so that is still way above the ground state. But you have learned just from Marcus that if the detection is basically quantum limited, so if you can monitor or trace the position of the particle really precisely, then that's a way to cool really to the ground state. There's one thing I will later talk about a little bit more, because it has to do with short range effects, and that is basically the interaction of such a levitated nanoparticle with the surface. We also looked at rotation. So if these particles are non-spherical, you can actually see that they also rotate, and you can control the rotation. And some of you here in this talk, so Markus Arndt and James Millen in Vienna, they basically showed beautifully how you can control the rotation and different rotational modes of these particles. And we did some demonstration of precession motion of such particles in a trap. Okay, so that is just this one slide to give you a flavor of experimental possibilities, so you can really see it as a resource of, it's a toolbox which is growing, and there's a community. Many of them are here in this audience, We are getting better and better as a community in controlling actually the motion and the rotation of these objects. And we are very hopeful that can be used to test fundamental physics, and I will illustrate some ideas. So that is, I just wanted to mention it to link to discussions on the first day. So that is our take on preparation of a spatial superposition state. So that is an interferometer, a Talbot interferometer, very much inspired by Markus Arndt's molecule interferometer experiments, now applied to this nanoparticle case, where it starts with a trapped and cooled nanoparticle, and it goes through a phase grating, and you can hopefully see interference pattern. And we are aiming for moderate 1 million or 10 million atomic mass unit particles to see interference pattern. Okay, good. So then the next one is, I should also mention this, that I basically spend a lot of time to think about collapse models, so like the CSL model, but also gravity versions of collapse models and how they can be tested. So it's clear that if you generate a spatial superposition state, then you can probe into those models and predictions of those models, because they predict that you should not be able to do it at a very specific point depending on the model. Now we know that is and it has been discussed here in this meeting quite a lot already, that generating such superposition states, spatial superposition states, it's quite difficult. So we were looking for an alternative method, and that is what we now call non-interferometric methods. So you basically look for the noise which is predicted by these collapse models, so not predicted as a physics effect, just as a mathematical mechanism to actually collapse the wave function. And so that's quite interesting, because you see that there's a broad class of different experiments, including gravitational wave detectors, which actually can set bounds on those collapse models. I think in general, the take on probing physics in this way is really looking at the noise and asking the question, what kind of fundamental noise can be out there? We know already there's the cosmic microwave background, CMB. Are there other type of noises? So therefore, I was very interested to hear about the gravitational noise and the noise of the gravitone, which is a specific noise, if you want, which can be predicted and calculated, and it should of course couple to the systems. And what we have done in the context of these collapse models is basically ask the question, how is noise, such fundamental noise, affecting these optomechanical systems? Okay, good. So that just to mention in passing. Now here's this experiment which I wanted to show you in some more detail. What we are doing, there's a cartoon here on the left-hand side. We levitate optically a nanoparticle, and what is not shown is that the light is actually reflected here in the parabolic mirror, which is focusing, and in between the trapping position and the mirror, we have now a surface which is a silicon wafer, just the same kind of wafer which is now used by micro electronics, nanoelectronics, nanofabrication. So that's a single crystal, and we have done the experiment in a way to, let's say, reduce the optical interference effects between the particle and the surface, and to really probe into the surface interaction. So how much is now this nanoparticle interacting with the silicon surface? So you can think of this as an levitated atomic force microscope, if you want. And of course, the force resolution is much better than what they had when they did the first AFM experiments. So what we were interested, of course, is to look into Casimir and van der Waals type interactions, because that is what we have learned from these proposals with Sugato and many other colleagues and friends, that is something, if you're interested in probing interactions between particles, you run into those interactions which you have to somehow control, and you can use screens and all of that. And we just wanted to see what is actually an interaction. So what is shown here is basically now the effect. So if you bring the surface, you make this initially harmonic potential unharmonic. So that's the effect of the interaction with the surface, if you want, in the phase space, and that's the data which George took at the time. You go from like a spherical distribution for a thermal state, you go to this kind of elliptic one, which is now telling you that the force is there, and you can basically from there you can extract the strength of the force. And what we found is that it is not even Casimir or van der Waals interaction, which we see. It is actually Coulomb interaction, because the particle carries an electric charge, and it interacts with its own image charge in the surface, and that gives the best fit as a model to our experimental data, which was done together with Stefan Buhmann from Freiberg. Okay, so that is just to give you a little piece of experimental reality. Yeah? So there's also charge sitting on these particles, and if you're interested in probing interactions on a short range, so you have to think about it. And luckily, there is now a different tool set, and I'm sure Peter will talk about this tomorrow. How to control electric charges on those nanoparticles you can add and you can subtract, and you can keep it actually fairly controlled. Okay, so what is next? Next is now for something completely different. We had a proposal, and I'm sure we will talk about this more today, later in this session, and maybe also tomorrow. It can be, if you have this levitated particle, then it of course interacts with all sorts of things, and if there is dark matter of a specific type, then that should show a mechanical effect on your particle. So basically, the idea is you trap your particle, and the dark matter is coming in as a sort of noise, and you see a Brownian-like motion of the particle as such. And in this proposal here, we have basically worked out numbers of the experiment to be sensitive to see a specific low mass dark matter particle, which we also predicted to be at 100 electron volts. So there are a lot of assumptions in this work, but I hope some of you maybe find it interesting. There's of course another effect. If you have a superposition, then also this dark matter can be another decoherence effect, which should basically kick in at some point. And the original idea, of course, goes back to Jess Riedel, who came up with this. And we also looked at this in some more detail and calculated how the decoherence, dark matter would decohere a spatial superposition state. Okay, so let me see what is next. Now there is basically this part of my talk where I talk about different ideas of gravity, and I have to say that is by no means systematic. So I basically take whatever comes in terms of gravity, and I just ask the question, okay, so would we be able to see this specific predicted effect in these experiments? So the first example is this semi-classical Schrodinger-Newton equation. And I will not go much into detail here. It's a semi-classical gravity idea, and what is maybe a familiar way to write it down is in this frame here is that you have the Schrodinger equation where you add Newtonian gravity terms. There are a lot of problems, faster than light signaling and these things, because it's in 1/r potential basically, which you have here, and it's known that this has this effect. But nonetheless, you can ask the question: what is it? What I have to do to see the predicted gravity of the Schrodinger-Newton equation, and especially the self-gravity. So now the weird bit of this model is, of course, that you have a completely different interpretation of the wave function. So you somehow assume it is also a mass distribution, which of course is, many of you will fundamentally completely disagree with this, and I'm fully aware of that. But just for the sake of checking the numbers, the way to do this experiment would be, of course, you have a wave packet, a wave function, and you just let it freely evolve. Yes, you would need a very long free evolution time for the wave function. And you ask the question: is there, some situation when that is the wave function of a very massive object, of a very massive particle, that the wave function would basically contract again? So it would basically gravitational, attract itself and would shrink in size and not disperse as it's, the usual evolution according to the Schrodinger equation. And you see that is a tricky experiment. If you do the numbers, you need a very large mass, and you have to much probably go to space to do it. So what we did with André Grosshardt, who is a theoretician working on the Schrodinger-Newton ideas, is to look at an harmonic oscillator, basically an optomechanical system, a massive object, and you go to the ground state, and then you basically measure the spectrum of this harmonic oscillator. You maybe want to make it anharmonic to see a bit more, which you can do by an additional force. So you make the harmonic potential in a more like Morse potential one. And then the Schrodinger-Newton equation basically predicts that there should be a change in your energy levels compared to the pure mechanical oscillator. And now Markus told us that they have reached the ground state. They could in principle try to do this experiment and see what is the the level structure of their harmonic or anharmonic oscillator. Okay, that is this idea. I know I'm very slow actually in progressing here, so I will try to make it faster. Also, this idea, of course, has been discussed many times already in this workshop. So Feynman or Bronstein's idea, what is actually happening if you have a massive superposition and you probe it with a second system, and Vlatko also talked about. So the quantum expectation is, of course, to see this bimodal distribution, if you want, so to get basically one by one, if you repeat this many times, this experiment, to get these two blobs as your expectation value for the experiment. While if you assume something like a Schrodinger-Newton equation, you would basically get a completely different result of this experiment. So that makes it interesting to actually try it. So there's like a different prediction from a classical gravity theory to a quantum one. Just for those amongst you who maybe still consider that there is, a classical gravity as a fundamental thing in nature. So we looked into this with Mauro and with Matteo and Angelo, and came up with the proposal. So that is, again, just putting in numbers and see if that can be reached. And we think, yes, it is not completely crazy to try to do this experiment actually based on optomechanical systems. I will not go too much into detail. We also think that a certain angular superposition state, where you have you use basically the power of rotation, not in the sense of free rotation, but in the same sense as Cavendish used it. And you also saw that in Markus's experiment, in the two-mass gravity experiment, that there is actually a pendulum, a torsion pendulum type of oscillator, and that is very, very good from an experimental point of view, because you can actually use it to avoid a lot of noises which would otherwise, or accelerations which would otherwise basically move the center of mass of your two-mass system. So the same idea we try to implement here, and what you actually find is that you still need the situation that your system is free and can freely evolve. So any potential which you use to trap this angular system will have a much stronger effect than the effect of gravity. So that means you also have to do this in free fall. Again, that is just a very brief mentioning of this idea. There is a paper out there which describes this, and I'm happy to talk more about the experimental details if you're interested. That is like the main proposal, I think, of this conference. So I will not go and talk about it. We have already done it. Let me maybe now go to the magnetic levitation. So I told you we have this Meissner trap, or the Meissner levitation experiment. So here's the first version which we did, I think 2 or 3 years ago. We started with this. So there's a neodymium permanent magnet. In this experiment, it was 3 millimeter in size, so pretty macroscopic. And that is now levitated in the cryostat above a lead piece. So lead becomes a type 1 superconductor if you go below something like 9 or 10 Kelvin. So the trap is very simple. So you basically have the permanent magnet which generates a magnetic field, and then we know that the type 1 superconductor is an ideal diamagnet. So it basically responds with the exact opposite magnetic field. So it cancels, and that is what we use to trap. What you cannot see is that actually this the lead piece has a structure. So there's a hole in the middle which is basically used to shape the geometry of the trap. So that's how we get a spherical or an harmonic trap. Yeah. So these are numbers from the first experiment which we did. That was with optical detection. So very simple. Just use the visible laser scatter the light off this particle and then detect it with the camera or with the photodiode, and then see how the particle moves. And already there we could get quality factors of in the thousands, which is quite good. And that of course comes from the fact that this is a levitated oscillator, so there is no strong coupling in the sense of substrate or so to the environment. It's just the field, the trapping field, which is linking it very softly to the environment. Okay, so then we did a bit more advanced experiments, which use quids, so that is at lower temperature, down to 300 millikelvin. But the idea is still the same. So there is this permanent magnet, which has a permanent magnetic moment, and that is the lead piece, which has now more like a cup structure that defines the trap. And we couple to an antenna, which is coupled to a squid to detect the motion of the particle. So now if the particle moves, then of course the magnetic field is slightly changing also in position, and that is what is detected by the squid. Here you see the particle, so that's a microscope image. It's roughly 30 microns in radius, so 60 micrometer size permanent magnet. And here you also see the background is basically the top, the bottom face of this trap. So it's a machined lead piece, which is also polished. And actually, to get this, the surface right, that is actually the critical part of this experiment. Okay, so now with the squid, you can read the spectrum that is shown here. It's actually, if you have never seen a spectrum, that's actually a very nice one. What is also very nice is that you actually can identify what are the degrees of freedom you're looking at. So if I go back to the previous slide, you see that now this particle, of course, can move in what we call translation. So it can move in X, Y, and Z, but it can also rotate. And because there is now a magnetic moment, so you have basically a vector sitting on your particle, you can resolve rotations around different axes, and that is what you see. And then you can identify and characterize these different motional degrees. So that was an experiment at 4 Kelvin, moderate pressure, but we already have 10 to the 7 quality factor. And if you see the numbers below here, so that is now basically the estimation of our sensitivity, so the force sensitivity and the sensitivity to measure magnetic field, which is all worked out based on a thermal force precision measurement model. So we assume that our oscillator, which we can see from the spectrum, actually from the shape of the spectrum, that it is thermal noise limited, so that there is no other systematic effect which is affecting the motion of the particle. And then we can use this force noise equation to actually work out what the force noise is. And it is very small. So for torque, actually, so that is for the rotational motions, it's 10 to the minus 20 Newton meter per root hertz. And also, I hope you can see the number here. That was a remarkable result, is that the sensitivity to measure magnetic fields is on the order of femtotesla per root hertz. Yeah? So it is a very sensitive magnetometer. So
5 minutes.
Okay, so thanks, Peter. That triggered, of course, thinking and ideas. So now here's this idea to go into gravity and to do a 2-mass experiment. So if you want, that is the levitated version, or one levitated version of the experiment Markus just told you about. So the masses would be in a very similar range. We have basically one trap where we put one mass and where we shake it, so that that is now the source mass, which is modulated, and then we would try to pick up basically this modulation of gravity as a signal with the probe mass in the other trap. So there's superconduction gives you this as a present. There's basically this green here, it's superconducting, so that means that all electromagnetic interactions should in principle cancel to zero. So in reality, of course, that will not be exactly zero, but it is reducing it significantly. So you see here, these are the springs. They look very harmless in this picture, but that is actually the very tricky part of the experiment. So if you, for instance, work out in an experiment which is roughly 1 ton in a cryostat with a big granite block, and you shake this little milligram mass by, I don't know, 500 or 50 micrometer amplitude, then that acceleration which you get from shaking this little mass is actually larger than the gravity which you want to measure. So you better think about how you isolate these two traps from each other so that there's no mechanical link which can actually, get this mechanical acceleration travel over to this. So that is what makes these experiments like really complicated, as we have seen and discussed already a lot in this conference. So now you can look into gravity, and that is just, to give an example, if you reach the sensitivities, so that's very similar to what Markus has showed you. If you have 10 to minus 10 meters per second square acceleration, which you can measure, then you can look at non-Newtonian gravity or deviations from Newton. In again, if you allow me to use this simplistic view on gravity, of course, then many other things are predicted to happen there, like depending on the interactions which you allow between the particles. I should maybe really come to an end, maybe just as the very last one, I promise. What is interesting with this levitated magnet here, you can also try to do like a ferromagnetic gyroscope. So you can do, and that is work which we have done together with Dimitri Budka and Derek Kimball and Sasha Sushkov. And the idea is that you basically have your levitated magnet here. So you have this magnetic moment, and then you apply an external magnetic field, a constant magnetic field. And then what you should see is precession motion and all the other motional degrees, which are illustrated here. So you have precession and nutation and all of that, and they are very sensitive to sense exactly this magnetic field which is causing it. So now if you apply it, you can also, and just to mention this, you can think about using this to detect, again, a different type of speculative dark matter particles, axion-like particles, which now not interact with the magnet by gravity, but by a dipole-dipole electron spin interaction. And we have worked out basically, again, numbers, how that can be tested. And that is an exclusion plot here, which is shown. And I finish now, and yes, thank you for your attention. Thanks.
Okay.
I stop without conclusion.
Thank you very much, Hendrik. Any questions? I see claps. I'll get in a quick one. So can you tell, so I know, these eddy currents can limit what you do. Yeah. Can you talk a little bit about that, where it would limit things and where it wouldn't?
Okay, so that is, of course, like, in this magnetic business, that's a serious thing. So whenever you have like a piece of metal or anything where you can have, a current in, yeah, and that is close to your magnet, then you have these eddy currents, of course. And we have, in the very first experiment, the one where we detected optically the motion of the magnet, you can see on the picture, maybe I can show it again. You can see that there is, like a metal clamp here, which was used to actually hold the lead piece in position before it was frozen by the ice, which was also in the vacuum chamber. That's a funny movie, because there's an ice cover on one half of the sphere, so you see that the particle is actually doing like a nice pendulum motion. But ultimately, the quality factor which we see of 5,000 or so is limited by eddy current which is induced here in this blob. That is known, and one basically has to build a geometry where there is no piece which can have an eddy current in. Yeah? So that is why in the later experiments it's a cup which we also close on top. With the lead block, and there's only the pickup coil which is inside. That's the only thing you need, and that's the other tricky bit in this experiment, is actually that you need the squid pickup loop pretty close to the magnet to actually get the signal. Yeah, so that is
okay.
It's a balancing act.
Yeah. Okay. Thanks very much. So Andy Geraci and then Sagato, I think.
Hi, very nice talk, Hendrik. So just a quick question on the results you showed with the gravitational test using the levitated masses with the magnetic effect. So you showed a plot. I don't know if you can go back quickly to the showing the limits for Mond versus or Newton. Yeah. So I'm just wondering. So gravity has been, reasonably measured at this sort of distance scale at a few millimeters, and so would this be consistent with the, say, torsion balance experiments that have looked at, say, either the Newton constant or inverse square law at these distances, or would those have already ruled out these Mond modifications, or is there how is the work here, I guess?
Yeah, so that's an interesting question. So we have just recently started to look into this with some colleagues from Southampton who are more experts in the gravity side. And so it seems that also the torsion pendulum experiments, they should have measured something in that range, right? Because they're already there. So there is something which I think maybe some of you understand better, which is with this Mond, so with this specific non-Newtonian gravity models, which is actually interesting. It's not the modification of Newton's gravity, but it's a modification of Newton's second law, so of the force law. So you should be able to measure this with any force, not just with gravity. And that's typically, of course, used in on astronomical scale. So the most severe tests of this Mond models come from astronomical observations of big masses moving in galaxies and things like that. Yeah, and there's also an argument that it is very tricky to actually do it on Earth because you need a specific configuration of the mass. So and then you have to. So I think one needs to think a little bit more about this. Yeah, so that is just the first naive, just using a simple equation and looking at. Where should we be able to see a difference, and then look and do some more sanity checks. Yeah? That is basically the level of where we are. Yeah.
Okay. So Sagato, I think we better stop it there and continue on, and we can have further questions at the end of the session. So where are you, Sagato? Are you? No, sorry, Sagato was saying that you could have a quick
You did tell me to. Okay. I thought we were continuing the. Yeah. So like this time, yeah. So it's a very, very interesting talk. Obviously, it's a lot of things. So Hendrik, so I was most interested in this femtotesla per root hertz. Your measuring ability. Also, these are very required for our Stern-Gerlach interferometry in turn. We require to know the magnetic field that well. Now, how much region does this thing cover? Like when you're saying you're measuring magnetic field to this accuracy, does it, how much spatial region does it cover? Or can you use it really as a sensor for another experiment in the box, like what magnetic field fluctuations are there?
Okay, so the region which you probe is of course the size of the particle, right? And that is let's say 50 micrometer or 100 nanometer in diameter, right? So that is that's the space where you look at, and then of course it's moving a little bit, yeah. So the amplitude of the oscillation, that is the space where you see it. Actually, the detection of the magnetic field is very interesting. So also Dima Budka, when they did a similar experiment with the type 2 superconductor, and so they had some issues with flux pinning and so it was not a high Q experiment, but they also already saw that it can actually measure very small magnetic fields. Yeah? And then if you naively put in numbers and you compare it to things like the standard quantum limit, and you see that it outperforms this standard quantum limit by 2 orders of magnitude. Yeah? So something has to be wrong. And I think that the thing which is wrong is that, of course, you have the magnet. It's a macroscopic object, and the magnetic moment is like a polarization effect of many spins. So there are many electron spins which are basically aligned in domains or so in a specific direction. And I think also in early optics experiments, people were thinking that they can outperform SQL easily, but also there it was not like a single let's say a single photon or a single spin experiment. Right? So of course you only have the problem of SQL if you probe the same system
Again,
more than once, right? If you have an ensemble of many spins, then of course you only do a measurement here and then another measurement on a completely different spin. So that does not apply. But as an fact for a measurement is that compared to other magnetometers, that is quite competitive. So it's a classical system. So there's no, if you say the spin, of course, is a quantum degree of freedom, but as such, it's a classical mechanical oscillator. And that is quite competitive as a magnetic field sensor if you even compare it to atomic cells or things like that.
Okay, I think we better keep on going. So thanks, Hendrik, for your nice talk. And let's move on over to Dave Moore. Do you want to show us your screen? So off you go, Dave.
Yeah, great. Thank you, Peter. And yeah, thanks to the organizers, Anupam, Sugato, and Andy for organizing this great meeting. I think it's really inspiring to see the kind of level of ambition of some of the things we're thinking about this week. So this has been really fun. So I'll be telling you about optical levitation we're doing in our lab, and in particular, focusing on the kind of larger mass scale with which you can do with optical levitation. So a bit smaller than the masses, quite a bit smaller than the masses Hendrik was just talking about. But kind of, we think, at the upper limits of what might be possible with these specific techniques. So just to kind of motivate this, I think as everyone here knows, if you build in optical tweezers, you can levitate kind of nanogram scale masses. So these are micron scale masses with densities of a few grams per centimeter cubed that you can levitate in an optical tweezers with milliwatts of laser power. And in our lab, we're using the levitation trap, just like the original trap built by Ashkin and Zeechik all the way back in the 70s, because it really uses the minimum optical power you need to optically levitate something against Earth's gravity. And maybe just to put that in some numbers somewhat relevant for this meeting, the mass you can levitate in these style of traps is something like 1% of the Planck mass per watt of optical power. So that's maybe 200 nanogram masses per watt of optical power. So you're really not going to get much of, going to the Planck mass here, you need hundreds of watts. And the real challenge there, if you did want to do this, it would be much smarter to do it with magnetic levitation. But if you did want to do it, as I'll say in a second, we don't have optical materials that are low absorption enough to really push up to extremely high masses. So these techniques are nice in the nanogram scale. You can just take a single vertically oriented laser, focus it, and trap a nanogram particle just above the focus. And then you have all the tools that you have with, optical physics to be able to, modulate this optical potential, turn it on and off. So for practical applications, it can be, there can be some advantages to using optical levitation, especially if you're going to use, a laser to read out the position of your object anyway. You're already blasting it with lots of photons, and at these mass scales, actually the number of photons you need to kind of measure these things near or approaching the standard quantum limit are roughly what you need to levitate them anyway. So this can be an appealing technique. Of course, as we know, one of the reasons to use levitated masses for all the things we're talking about, and it's really crucial, is that we can extremely well isolate these masses thermally just by pumping the gas out of the chamber. But I'll say this and come back to this. It's also kind of crucial that you can electrically isolate these masses so that we don't have charges flowing onto and off of the masses, and we can control their charge state extremely precisely. And I'll come back to this at the end of the talk. We've already heard this. This is the short distance force session, so it's not surprising it's coming up a lot. But often a key challenge for realizing some of these really ambitious ideas of what to do with these types of masses is, we've talked a lot about more fundamental sources of backgrounds, but there's non-fundamental sources of backgrounds just from stray charge and other things like that. That can be a real challenge, even though in principle we can overcome them if we're careful enough. So before I tell you a bit about the experiments, let me just show you the team that's doing the work. So we're a relatively small team, but as I'll say, we're doing we're looking into particle physics style questions. So we have an acronym, but we're a group of about 8 people working here at Yale. And I should just highlight that we have postdoc positions available if anybody's interested. This is the setup in our lab, or one of the setups in our lab. It's an optical trap with optical tweezers and vacuum, one of these vertically oriented gravity stabilized levitation traps. It allows us to trap spheres in the same trap with really no modifications over a pretty wide range in masses. I'll show this on the next slide, but from about 0.5 micron in radius up to 15 microns in radius. And this upper range I'll come back to is limited to just heating and eventually melting the spheres. In the middle of this range, we maybe need only 100 milliwatts of trapping laser power to levitate them. And once we have them trapped, these are really stable systems. We've had single spheres trapped for kind of month-long time periods at our current base pressure around 10 to the minus 8 millibar, sitting there in the trap and able to perform measurements with. So kind of maybe the thing that sets this talk apart from many of the other groups working in optical trapping and vacuum and levitated optomechanics is the large size of the masses. And large here is in quotes because it's really this nanogram scale I was talking about. But as I was saying, using this kind of gravity stabilized levitation trap, we've demonstrated at least the levitation and vacuum of the optically levitated most massive objects to date. This picture at the top right here is just showing in the same trap at exactly the same height, we can trap kind of over several orders of magnitude and mass from 0.1 nanograms up to 10 nanograms, different size silica dielectric spheres, stably, with minimal modifications to the setup. The only thing that limits us from going higher, we can actually trap even larger spheres at atmospheric pressure in moderate vacuums, but as we lower the pressure in the chamber and the only cooling of the object starts to be black body radiation, then if there's any trace optical absorption of the laser trapping light by the object, then eventually it'll heat up to above 1,000 Kelvin and vaporize in the low pressure of our vacuum environment. And we've actually trapped even larger objects than this, pumped down the chamber, and seen them reduce in size as the outer layers vaporize off. That said, these materials that most of us use are colloidally grown silica that have actually much higher optical absorption than a high quality fused silica would. So if we can improve the optical materials we're trapping, you may be able to push a little farther and go up to the kind of hundreds of nanogram scale. But as I said, beyond that, it probably is not feasible with these techniques. The reason, though, that we're focusing on optical trapping of these large objects is we're often interested in the sorts of things we're talking about this week in our applications. So measuring forces that couple to mass or number of neutrons or other quantities that scale with the volume or mass of the sphere. And so really the figure of merit for many of our searches is acceleration sensitivity, so force sensitivity per unit mass. Of course, you can get to extremely low force sensitivities by using very tiny objects, but for the things we're talking about this week, often what you're sensing is accelerations. And for one of these optically trapped kind of nanogram scale masses, we can get down to sensitivities around an attonewton per root hertz on the force sensitivity side, or 100 nano G, where little g here is Earth's gravity, per root hertz on the acceleration side. And that's in a single second measurement. And the other nice advantage of these systems is you can integrate for a long time. So here in several hours, we can get down to the zeptonewton force scale, or pico-g, hundreds of pico-g acceleration scale. And maybe just to emphasize this point, this is a plot from our recent summary paper we had with Andy, applying the acceleration sensitivity only of optically levitated systems. So actually the magnetically levitated systems will keep improving in their acceleration sensitivity as you go to even larger masses. But these systems that we're building at Yale here at the nanogram scale are pushing down, substantially lower in acceleration sensitivity than is really feasible with the much lighter masses. So the kind of femtogram masses, the 100 nanometer sort of particles we heard about from Marcus and Hendrik at the earlier part of the talk have much better force sensitivity, but in the acceleration figure of merit sit somewhat higher on the plot. So once we have these trapped at low pressure, the other thing we want to do is cool them down. And we've also worked to be able to cool these large nanogram scale masses to relatively low temperatures. So this plot here on the left is just showing the power spectrum of the displacement in meters per root hertz versus frequency. We have both an out of loop and in loop sensor for one of these trapped spheres. And you can see in the purple line here with relatively low damping in our feedback loop. And this is done with active feedback, just like Marcus was talking about in a part of his talk earlier today. We have a relatively high Q feature here at the natural resonance frequency. And then as we increase the gain of our feedback loop and damp more and more of the particle motion, we move down to these colored lines, and at the maximum gain, we're getting down to effective temperatures for the center of mass motion around tens of microkelvin, so something like 50 microkelvin. And this is just showing on the right plot here that as expected, as we increase the gain more and more, we get down to lower temperatures, but then at some point, this out of loop sensor hits a floor, which is just that we're starting to squash noise and no longer cooling the motion, even though the apparent noise in our in-loop sensor keeps getting better. So this is a relatively low temperature. I think it is maybe the lowest temperature for this this scale of optically trapped mass. But we're still quite far from the kind of ground state things that we heard about from Marcus with the femtogram scale objects. KT over h bar omega here is something like 10,000. So we're quite far from being anywhere near the ground state. But this is still limited, I'd say, by technical noise in our system, and we have some good ideas for how to keep pushing that technical noise down and keep pushing lower in temperature. Okay, so in addition to cooling, I said the other really key, and being able to isolate extremely well the center of mass motion of these objects from the thermal environment, we're also able to electrically control the charge state of the objects extremely well. Hendrik also mentioned this, but we just can take, in our traps, we position the microsphere between two parallel plate electrodes, apply an oscillating electric field, and then just monitor the response of the sphere to that oscillating electric field. There's a net charge on the sphere, of course, it feels a large force, and we can monitor its response to that field to measure its net electric charge. And so that's shown here on the plots on the bottom, where we're just plotting the net electric charge of the sphere in units of electrons. So this is a negative net charge. Our large spheres actually typically start out with a pretty high electric charge, so more than 10,000 electrons electric charge. We flash the region around the trap with UV light and knock electrons off, and actually can substantially discharge them here in the scale of tens of minutes. In this case, we actually go past zero, which means we have an excess of protons in these units, so more protons than electrons on this object. And then we actually just change the configuration a little bit, so we're knocking electrons off of the gold plates onto the sphere instead of vice versa. And then we're actually able to charge the other way. And if we zoom here at the very end, you can see these single electron steps that corresponding to just adding one electron at a time until we get to an exact integer charge of zero. So exactly the same number of electrons and protons on this nanogram-scale object that has something like 10 to the 15 electrons and protons in it. And this is done in a relatively low electric field. So each of these steps here that you're seeing with quite high signal to noise and just a second measurement correspond to something like 200 attonewtons. In addition to controlling the center of mass and electrical degrees of freedom, the other thing we've done relatively recently is work to control the rotational degrees of freedom. We've already heard about this in the meeting so far, and I think we'll hear from Tong Chung again tomorrow about it. In our case, we're able to actually optically rotate our spheres that we trap in high vacuum up to kind of megahertz scale frequencies, and this is really just limited by the yield strength of the material. If you spin the sphere too fast, at some point the centrifugal stress overcomes the yield strength and the sphere blows apart. So for these micron-sized objects, megahertz and the strength of silica, kind of these megahertz frequencies are attainable. And it turns out that when you get to the extremely low damping conditions of ultra high vacuum or high vacuum, really, so in this case, we're doing this at pressures of 10 to the minus 7 millibar, the even extremely tiny torques from stray amounts of birefringence or absorption are enough to spin the sphere up if we trap it in circularly polarized light. So we just trap a silica sphere in circularly polarized light, and then over the course of a day here, so this is 80,000 seconds here on the horizontal axis, we actually see that silica sphere spin up faster and faster to, in this case, just above 4 megahertz. And it spins up very stable, just like you'd expect if from just pressure limited damping. And in fact, we verified that the damping for this free rotor degree of freedom just follows one of the pressure, as you'd expect, over a wide range in pressures for these spheres. So I'll come back to this later in the talk, but this is really crucial actually for once we've controlled the monopole state or the net charge of the sphere, controlling the higher order multipole moments of the electric charge distribution. And so we were able to do this even with the amorphous silica spheres. This had been done many years ago with highly birefringent spheres and moderate vacuums, but as you get to low vacuums, even these spheres that are not intrinsically naturally birefringent will spin this way. And then again, because the centrifugal stresses are lower in smaller objects, Tong Cheng's group and Lucas Novotny's group are able to spin actually these 100 nanometer objects to gigahertz and several gigahertz rotation frequencies. So you can really spin these things incredibly fast, and then this spin stabilizes the rotational motion, which can be important if you have some coupling or error in your imaging between the center of mass and rotational degrees of freedom. Okay, so in our group, we're interested in now taking these systems and applying them to testing fundamental physics. Many of our interests are actually a little bit different than the focus of this meeting, so somehow maybe more conventional tests of particle physics or fundamental physics. So there's lots of things you can do. I've listed some of these here. I'm not going to talk about all of them. I'll just highlight a couple, but I'll just advertise quickly that, of course, you can, some of the original motivations, going back to an early paper from Andy almost a decade ago now, is to test Newton's law at short distance. We'll hear about this later today from Chaz Blakemore in more detail. And so we're also working on testing Newton's law with putting these objects close to a modulating mass density. In our case, that mass density is made by varying density fluid passing in a microfluidic capillary that we can stick right next to the sphere. We're also, working on designing tests of Coulomb's law at short distance to look for, deviations from Coulomb's law that could arise if you have something like a dark photon, or dark matter has new gauge forces that can weakly interact with the standard model photons. I will talk about some recent results on the neutrality of matter. So once you have this object with something like 10 to the 14 or 10 to the 15 electrons and protons in it, and you have exactly the same number of electrons and protons, you can ask, is that object exactly electrically neutral? And there's some motivation for looking for dark matter particles that could have tiny electric charges. So I'll talk about that in a second, but also testing quantization of charge. So the sum of the proton, electron, and neutron charge, which we know experimentally with extremely high precision to be exact, less than actually 10 to the minus 21 electric charges. But since we don't know of an underlying symmetry between the quarks and the leptons, that's actually still somewhat of a theoretical puzzle in the standard model, and might require some higher energy unification or something that we haven't yet observed. So it's always an interesting thing to test if we can test it better. And then recently, we've also been trying to see really tiny impulses, so small momentum kicks to these spheres. So over the summer, we published a paper looking for actually dark matter particles to hit, scatter off the sphere coherently via long-range force, give it a kick, and observe, the momentum kick imparted to that sphere. It turns out that even with these kind of nanogram masses, you can see momenta transfer as small as kind of hundreds of MeV per C. So really particle physics units for the impulses. And so it turns out that if you can implant some nuclides that can decay by nuclear decay into the spheres, we could actually see the momentum kick from a single nuclear decay occurring in our sphere. So we're currently working on implanting actually radon daughters onto our spheres to, for example, see an alpha particle fly out of the sphere and see the corresponding recoil of the sphere as it flies out. But I won't have time to talk about these. So in the last few minutes here, let me just focus on this recent search we did for these millily charged dark matter particles, and then also say something maybe about the main theme of the meeting, which is challenges, and with emphasis on the challenges for some of the really ambitious things we're talking about here. Okay, so let me just advertise this quickly. So at the end of last year, we posted some results searching for millily charged dark matter particles. The models here are that dark matter is dark, so we usually think of it as not having an electric charge, but it can have charges. Dark matter could interact under forces with itself, with other dark matter particles, and even if those forces don't directly couple to our standard model electromagnetism, generically you can have these weak kinetic mixings at the Lagrangian level between the force carriers and the gauge bosons in the dark and the visible matter sector. So these kinds of things show up somewhat naturally, and you can in this case then have effective or tiny effective electric charges showing up on dark matter. If you did have a small electric charge for the dark matter, then you might expect it to actually form stable bound states with nuclei. And in fact, as the Earth sweeps through the dark matter halo, we expect these dark matter particles to be thermalized in the atmosphere or in terrestrial materials and get stuck in atoms. So there's a little schematic down here where you have some silicon nucleus maybe in our sphere, positively charged silicon nucleus, negatively charged dark matter particle, which forms a Bohr-like atom with that nucleus. And there's this paper from the summer talking about, in some detail, calculating what the abundance of such particles should be if the Earth is sweeping them up from the dark matter halo. And this plot from that paper is just showing the region over which you can form these stable bound states. So the binding energy of this is larger than thermal energy, or sufficiently stable that you can actually form these and search for them. And so for instance, for this positive nucleus and negatively charged dark matter particle, you have some fairly wide range of fractional charges and dark matter particle masses over which such bound states can form, and also corresponding actually to a gap in parameter space where our existing searches for fractionally charged particles haven't yet been sensitive. So the goal here then is to do this with microspheres, look for these kinds of tiny fractionally charged particles stuck in the microspheres once we get them to this completely neutral charge state. Okay, so the challenge, of course, to these experiments is not so much the sensitivity. I mean, you can write down the force sensitivity we have. We can apply a 10 kilovolt per millimeter electric field in the vicinity of this perfectly neutral sphere, and we expect actually to be able to get to extremely tiny fractional charges, or actually test extremely well the sum of the proton, neutron, or electron charge. But in reality, when we do the search, more mundane things completely limit the sensitivity. So we're nowhere actually close to the fundamental sensitivity that you would write down when you're starting out these searches. And I mean, maybe this is one thing to highlight. Of course, I think the goal of this community should be to really push the limits of these systems so we can get to those truly fundamental things that most of us have been discussing this week. But on the way there, there's lots of much more mundane things to overcome. And so just as maybe a worked example, I'll show you for this search, a couple of the backgrounds that ended up limiting the search. So even though our spheres have exactly the same number of electrons and protons, so their monopole charge is 0, they do have higher order multipole moments in the distribution. So we have 10 to the 14 charges in this object. And even if a few of them are offset from the center of the charge distribution, or it's not perfectly spherically symmetric charge distribution, we can have extremely large, by the scales we're talking about, forces acting on either permanent or induced dipoles in the spheres. So this is actually why this technology to rotate the spheres and control their rotational state is so important for this search. And so before we can even begin, so we're applying an electric field that's something like 10 kilovolts per millimeter to this neutral object. But we also need to spin this at megahertz frequencies. And we actually, if we measure the apparent charge or the apparent motion, the force on this, the real force on the sphere in that oscillating electric field as a function of its spin frequency, we actually see very large forces on the sphere when it's not, apparent forces on the sphere when it's not spinning, which can be reduced by orders of magnitude by spinning it up to these megahertz frequencies. And what this is just that there's a torque from this electric field on the permanent dipole moment of the sphere, or induced dipole moments that are lagging the phase a little bit, the phase of the applied electric field a little bit. And those torques are able to, rotate the sphere around. And if the sphere is at all aspherical, then we pick those up in our center of mass imaging as apparent motion of the center of mass. So by spinning, we're able to make this torque background negligible. The next background we saw then was vibrations. So actually applying the electric field in our chamber shakes around the whole electric chamber. So there's a electrostrictive force in the feed through of the high voltage supply going into the chamber, which shakes the front window of our 2 centimeter thick stainless steel conflat window by some tiny amount, which is enough to shake around the trapping beam and move around the sphere. So we're able to measure these vibrations actually by applying a separate monitor beam right next to the trap and measure the transfer function or the displacement of those beams for the one that's interacting with the sphere, or the actual transfer function we expect for a real force on the sphere, and then this vibrational motion, which unfortunately for one of our sphere sizes actually had a resonance quite close to the measurement or the natural frequency of our sphere. But we are able then to measure this with this monitor beam and deconvolve these vibrations, so they're also negligible. But then the thing that really limited how well we could do with this search was actual, not torques, but forces on the dipole moments due to stray electric field gradients. And so even though we tried as well as we can to really minimize the gradient in this perfect electric field we're attempting to apply, we can't do that perfectly. Any real system is going to have some tilt in the plates or inability to trim away electric field gradients, and those can couple to any residual dipole moments. So we are able to minimize this effect by measuring these electric field gradients in situ, and they match reasonably well what we expect from a finite element simulation. But in the end, we aren't able to completely eliminate these at the level we'd like to for this search. That said, you can still set some constraints, and I'll just go through this quickly, maybe because it's not the main focus of this work. But the first tests of the abundance of such fractionally charged particles in matter versus their fractional charge we published all the way back in 2015, and then now we've gone something like 2 orders of magnitude farther in abundance. So able to search for these things bound in matter, forming these stable bound states, actually down to the smallest fractional charges at which they can form such stable bound states. But now testing, parts per quintillion or really tiny fractional abundances of matter, where even if only a tiny fraction of the dark matter has this type of charge, we would be sensitive to it here. And if you compare that then to the constraints from colliders and other dedicated cosmological searches, actually, again, we have significant complementarity where if these things did get bound in matter, we would actually be able to see them on a wide range of parameter space that hasn't been searched yet. Okay, so I'm almost done, but let me just quickly highlight this challenge I already talked about for this search and how it might be relevant to the meeting's topics. So I think really controlling the charge state of these objects we found is a key practical challenge, not really fundamental, but practical challenge in implementing sensitivities at the level we would need to do some of the experiments being talked about here. And as Hendrik mentioned, many groups are now controlling the net charge or the monopole charge of these objects to single electron precision, so we can be really sure we have exactly the same number of protons and electrons. That's kind of required for any of these things. If you don't do that, as Hendrik showed, and you get near a surface, there's really huge image forces. So there's lots of technology developed to do that, but we don't yet really have a lot of technology to control the higher order multipole moments in the charge distribution. And again, because you have maybe in these nanogram scale mass objects I'm talking about something like 10 to the 15 charges, really kind of trace tiny amounts of asymmetry in the distribution of those charges can have huge effects. And the reason is just what we've been talking about all week, that this, the equivalent fine structure constant for gravity is something like 40 orders of magnitude smaller than the coupling for the electromagnetic forces. So stray charge is a really big problem in these experiments. That's of course not fundamental, but if you take our measured permanent dipole moments, I think Chaz Blakemore will talk more about this in his talk, but we're measuring something like 100 electron micron permanent moments in these kinds of silica spheres we typically trap, and compare that to the gravitational, so the energy for the dipole interaction versus the gravitational energy. This is something like 10 to the 6 times larger, so you need to cancel this dipole-dipole force for two of these objects, even if you're spinning them next to each other, to extremely high level of precision, putting kind of these fiducial numbers from Sugato's talk. And a similar statement was made about the Casimir force. This one though falls off more slowly than the Casimir force, so you can't win necessarily as quickly by just putting the objects farther apart. Of course, you can put the conductive shield between these, but I think many of us who work on short range forces know that that's a whole can of worms by itself, and controlling the charge state of that conductive shield that you put in here might actually even be harder than controlling the charge state of these isolated objects in vacuum. So this is probably going to be a real fundamental practical challenge, not fundamental, but practical challenge as we go forward. But you can see that you really have to control the charge state much better than we've demonstrated, or the shielding of those dipole-dipole forces much better than we might know how to do at this time. Okay, so with that kind of caveat, I'll just say that, nonetheless, I think, as we start to develop these levitated optomechanical systems for all the sorts of tests we're talking about, if we're able to, get systems good enough to do these tests of gravity we're thinking about this week, there's really a huge amount of other physics you can do with this, as I said, that our group is really interested in. I think some of these searches are much easier than the test of gravity. So as we develop these really sensitive systems, there's lots of interesting physics to do on the way. We're already trying to do some of that physics and running into background sources that will really need to be overcome as we push further and further. But I think I'm really excited about the potential to approach the real fundamental limits of these systems and see what kinds of sensitivities we can get to. So I'll stop there. If there's any questions, I'm happy to answer them. Thank you.
Okay, thank you very much for that nice, clear talk. Any questions? Just scanning through people. So I have a quick question. I see Anna. Well, Anupam, you go first.
Nice. Okay, go ahead, Peter, please. No problem.
So my question was, so if you were to swap over, and I know there are technical issues with that, to say a gold sphere, because potentially I guess you could levitate that even optically with a different wavelength laser. Can you get rid of some of the things like permanent dipoles in that way?
Right. So yeah, in principle, you can use a conductive sphere to really control the induced dipole well. But what we found though, and I'm not showing this because it's still a bit preliminary, but there's all kinds of subtle effects at the trace levels that happen, right? So if there's any finite conductivity of your gold, then your dipole moment is going to lag the field a little bit, and your purely induced dipole in the direction of the field may not actually be, completely canceled. And I have a feeling that, at the level that we're trying to do things, I mean, you could plug in the numbers for that specific case, but, conductive spheres are going to have problems too. And, certainly when you get things close together and you're sensitive to the patches and, messy distribution of those charges on the surfaces of even good layers of gold, I think this community knows and has seen for decades that that's a really hard challenge. So,
right.
so maybe
no simple answers. No. Okay, Andy, quick question.
Yeah, hi, nice results, David. So just a quick question about your observed effect with the permanent residual dipole. Have you noticed any dependence on the size of the particle? I don't know if you've studied that in any systematic way.
Yeah, so Gadi, who's on the line here, has been studying that in lots of detail. We have some less in the published paper. We basically see that whatever we're seeing kind of scales with volume, as you unfortunately would expect our signal. Well, fortunately or unfortunately, you'd expect the signal in that paper to also scale with volume. And we think this is related to the thing I was just saying with Peter, where it's actually, there's some finite conductivity of the silica, allowing us to induce large dipole moments. And those induced dipole moments don't purely cancel for the torques. But the permanent moments that we've measured with different techniques tend to be somewhat smaller. So they tend to be hundreds of electron microns, and not necessarily, we don't have a really accurate measurement of how they scale with volume yet. It's certainly true as you go to the really small particles, these things probably scale down somewhat. But I'm not sure that anybody has measured it for the femtogram scale particles yet in great detail.
Thanks.
Okay, thanks. I think there are a few other questions. Should we leave them until the panel discussion afterwards, and continue on to Timothy's talk? Do you want to share?
Sure, I will share.
Okay.
Is this showing up all right?
Yes, no, that's perfect. Why don't you just go straight off?
Okay.
There.
Yeah, so what I want to discuss today is probing gravity non-locally with macroscopically delocalized atom interferometers. And for a summary of what I plan to go through, I'll begin with a brief review of large area atom interferometry, then talk about some experimental results on non-locally probing gravity with these large area atom interferometers, and also associated constraints that this can put on certain local classical channel models of gravity, where gravity would act as a classical as opposed to a quantum entity. And then in the latter part of the talk, I want to offer a perspective for pushing quantum systems to even larger scales with a particular focus on the MAGIS 100-meter tall atom interferometer that collaborators and I are building at Fermilab. And then finally, offer some thoughts on the potential possibility of using this MAGIS 100 apparatus for exploring the kind of work that Igor Pekovsky talked about yesterday, for using interfering clocks as a witness of general relativistic proper time. So as an introduction, for the work I'll be discussing here, it will pertain to a technique called light pulse atom interferometry, where we use laser pulses to act as the beam splitters and mirrors for an atom interferometer to split our atomic wave packet into a superposition of two trajectories, which are later recombined and interfere. And we can control the momentum splitting, the number of photon momentum kicks, or h bar k, where k is the wave number of the laser, by adjusting, for instance, the number of pulses applied during the splitting. And atom interferometers can be highly sensitive to a number of signals of potential interest, including, for example, gravitational accelerations, or in some cases, to time variations of atomic energy levels. And generally speaking, one can improve the sensitivity by increasing both the spatial separation between the interferometer arms, which I'll often referred to as the wave function delocalization, and also by improving the total measurement time. And so motivated by this, one thing that collaborators and I, as well as a number of other people, have been working on improving in recent years is to increase this both this wave function delocalization and the associated coherence time to try to boost such sensitivity. And so one thing that we had demonstrated was macroscopic scale atom interferometers, where the wave functions are delocalized over distances of multiple tens of centimeters for long durations on the order of a couple seconds. And these large delocalizations are aided by using many enhancement pulses during the beam splitters to increase the momentum splitting, and in this work up to 90 photons worth of momentum. And to illustrate the intrinsic high level of sensitivity to gravity one gets in such an instrument, an example that I often like to give is that these measurements were sensitive enough such that Earth's gravity gradient, which is often thought of as a fairly small effect, actually created a full 1 radian phase shift over only the 1 millimeter vertical extent of the atom cloud, which we were able to see. Now, of course, if one actually wants to measure a gravity gradient, a much better way to do that than looking for a phase shift over a small atom cloud is to actually take 2 atom interferometers separated over a baseline and then make a differential measurement between them to determine the variation in gravity over the baseline. And so another measurement that we did with these macroscopically delocalized atom interferometers was to implement such a gradiometer configuration. And another key advantage of this gradiometer configuration is that because of the differential measurement, many sources of noise, laser phase noise being an important example, will significantly be suppressed as a common mode. And we were indeed able to observe this suppression for our large-scale interferometers. And to benchmark the sensitivity of these large-scale gravity gradiometers, what we did is we measured the gradiometer phase response to a local proof mass. And so when we moved the proof mass in and out between a near and a far configuration, we observed on the order of a 1 radian phase shift, which is in line with what we theoretically expected. And we also mapped out the phase shift as a function of how high we launched the atoms, which also matched well with predictions. And so something I want to focus a bit more on in the first part of the talk is a particular measurement that we did with this setup, where we measured for the first time the influence of space-time curvature, or in other words, gravitational tidal forces across a single particle's wave function for the first time. And although in our experiment, we could derive the phase shift perfectly well just using the Newtonian limit of gravity, what some of the original theoretical papers on this effect nicely pointed out is that if one thinks about the effect from a general relativistic point of view, because in general relativity, we're very naturally thinking about coordinate changes and coordinate invariance, that really helps to highlight why the effect is actually significant. And the key point there is that gravity in a coordinate invariant sense is in many ways defined by its curvature. In other words, corresponding in our experiment to the tidal forces it induces, because in contrast to a local acceleration, these curvature or tidal effects represent an effect on the wave function that cannot be transformed away by making a coordinate transformation. And so, for this reason, in a number of papers in the literature, including the 2 cited below, dating back several decades, such curvature-induced phase shifts across the wave function had been described as the first true manifestation of gravitation in a quantum system in this coordinate invariant sense. And in this situation, the wave function, because of this curvature across it, can no longer be said to exist in a single local inertial frame where you could just boost away the effect of gravity, and fundamentally experiences gravity non-locally, because different parts of the wave function feel out different gravitational accelerations. And so dating back to these early theory papers, there had been interest in attempting to measure this effect, but it was just more recently that the matter wave interferometry technology caught up to the level where one could delocalize the wave function enough and make sensitive enough measurements that these tidal forces across the wave function could be resolved. And what we measured was such a tidal phase shift associated with our local proof masses. And something I'll also talk about is that there was some additional work, not that I was involved in myself, but some theoretical analysis of our work subsequently that showed how operating in this regime could place bounds on certain gravitational decoherence models. Just to say a few more words about the measurement, what we actually measured was a differential tidal phase shift between our two vertically separated atom interferometers, because we were making a relative measurement between the two. And there is indeed such a non-zero differential tidal phase shift because the tidal forces, or in other words, gravity gradients across the two separated interferometers induced by our test masses were different. And when we looked at our data for this gradiometer phase difference in response to the proof masses as a function of the beam splitter momentum, we saw that the data, the black points here, disagreed strongly with the calculation shown in the dashed black lines, where we artificially ignored the influence of these tidal phase shifts, but matched well with a full calculation that included the tidal contributions. And another interesting thing to note is that the phase shift that we observed could not be attained from considering just the local gravitational acceleration along either one of either the upper interferometer arm or the lower interferometer arm, which are shown respectively in red or blue. Instead, to calculate the phase shift properly, the information of the local accelerations along both arms, which are different from each other by a resolvable amount, contribute to the total phase shift. And since we're probing these two arms with a delocalized wave function, this is another way of saying that the wave function is a non-local probe of gravity. And so an interesting question one can ask is that, okay, we're non-locally probing respectively the acceleration along the upper and lower arms with our delocalized wave function. In determining the ultimate phase shift, how do we combine those two local accelerations that the two arms of the wave function are sampling to determine the final phase shift? And there's a nice theorem that Antoine and Bourdet had derived, which showed that in the limit where the gravitational potential across the wave function is approximately quadratic, one should take an equal weighting of the local accelerations along the two arms, plug this into the usual atom interferometry response function to acceleration, and that tells you your phase shift. So in our situation probed by the experiment, we equally weighted the upper and lower arms, which is perhaps the simplest thing one might have thought of. However, if in the future one can go to higher order curvature across the wave function, the situation can become somewhat more complicated, where you no longer have this simple equal weighting. And I think it would be interesting to try to measure these phase shifts due to higher order curvature across the wave function, which would allow us to enter into a new regime in which this comparatively simple picture that we just, the interferometer equally weights the accelerations of the two arms, so effectively looks at an average of them, breaks down. And what's exciting is I think that such measurements are within reach in the not too distant future. There's an interesting proposal paper coming out of Holger Mueller's group in 2012 that suggested to engineer the source masses to generate a potential that had two force-free points, but different values of the potential. And then if you were to levitate the two arms of your interferometer respectively at these different points, these higher order curvature effects would allow you to accumulate phase, but in a limit where for much of the interferometer, you're not experiencing a significant gravitational force. You could also have a reference interferometer just to cancel out common mode noise. And so it seems that with achievable amounts of mass, one could achieve such higher order phase shifts that are quite large, either with mass outside of vacuum or as proposed in the original paper with smaller masses inside vacuum at shorter distances to the atom. So I think this could be quite an interesting direction. The next thing I want to comment on is a paper that had come out on 2018 analyzing how our results with macroscopically delocalized atom interferometers with gravity gradients across the wave function could constrain certain models of gravity in which gravity is a classical entity. And to just read a couple highlights from the abstract of this paper, they say that these single atom interference experiments achieving large spatial superpositions can rule out a framework where the Newtonian gravitational interaction is fundamentally classical in the information theoretic sense, in that it cannot convey entanglement, and saying that the experiments indicate that if gravity does not, that if gravity does reduce to the pairwise Newtonian interaction between atoms at low energies, this interaction cannot arise from the exchange of just classical information. To say a few more words about this model, which is based on the Caffrey-Taylor-Milburn framework that Jacob Taylor nicely discussed yesterday in his talk, which I should note is distinct from the commonly considered DOC Penrose model. I'm sure Jacob had given a much more detailed description, but just to briefly summarize, the idea of this framework is that in this local classical channel, there's a pairwise continuous measurement with feedback, so that if we have a pair of particles interacting gravitationally, the model corresponds to the position of each particle is continuously measured and establishes a classical measurement record. And then information from this classical measurement record is used to determine the feedback force to apply to the other particle with which a given particle is gravitationally interacting. And then there's an associated decoherence rate that is sufficiently strong to prevent gravity from increasing the entanglement of the system. And in this model, in the model considered in the paper, the decoherence rate is proportional to the product of the tidal force across the wave function, and then also proportional to an additional product of the wave function delocalization. And so in effect, what one can say this amounts to is that different gravitational forces on different parts of the wave function are effectively providing which path information, which in our experiments, one can then calculate as is done in this paper, what the expected decoherence rate would have been. And then based on this, the authors showed that one could strongly constrain this model. And so one thing I should say that is very important is that while the paper concludes that our experiments do constrain this particular local classical channel model, which is one example of a model in which gravity cannot mediate entanglement, our results certainly do not show that gravity actually can mediate entanglement. That's an entirely different challenge to show that, which a number of people at this workshop have discussed. Finally, in the last part of the talk, I want to offer some future perspectives for increasing atom interferometry to even larger scales, and what this might possibly be able to allow us to further explore in terms of the interface of delocalized quantum systems and gravity. And I'll focus on the MAGIS 100 detector that collaborators and I are building in an existing 100-meter tall vertical access shaft at Fermilab. And this will build upon the work done in 10-meter scale atomic fountains that some of which I showed earlier. And the key goals are to study foundational quantum science at even larger scales, search for ultralight wave-like dark matter, and also serve as a prototype detector for mid-band gravitational wave detection in the range between LIGO and LISA that Igor Pekovsky had also talked about yesterday. One thing that I find very exciting and where I hope that these efforts will ultimately lead is to a global network of long baseline atomic detectors of this type. What I think is great that there are already a number of such efforts being developed around the world. I've listed some examples here. And I should also note that what we're doing with atom interferometry has some rather nice conceptual overlap with the proposal Igor talked about yesterday for optical lattice clocks and optical lattice atomic clocks in space. So I think there are some good opportunities for collaboration on technology development. Just to give a very quick overview of the measurement concept of MAGIS, how conceptually the sensitivity to gravitational waves and to dark matter would arise, it makes use of several essential features. First, that in a vacuum, light will propagate across a baseline between two atom interferometers that we make to act as clocks at a constant speed. Then secondly, atoms can be made to serve as both excellent clocks and also very good inertial proof masses, the latter point when the atoms are freely falling in vacuum so that they're not mechanically connected to the Earth. Then the measurement concept is that the clocks read the light transit time over the baseline. And then the way a gravitational wave signal would come through is it changes the number of clock ticks, which corresponds to really a phase difference between the clocks associated with this light transit by actually modifying this light travel time across the baseline, which one can think of as stretching and contracting the baseline. On the other hand, dark matter would leave the light travel time the same, but it would still change the number of clock ticks associated with the transit for certain types of dark matter, modulating the clock frequency, in other words, the atomic transition frequency. And then finally, many pulses are sent across the baseline to coherently enhance the signal, which due to the momentum exchange with the laser field when we absorb and emit photons corresponds to large momentum transfer. And an important aspect of this measurement concept is that we perform atom interferometry on the narrow optical clock transition of strontium, which has a long-lived excited state, which allows for long-lived superpositions of ground and excited states with a large energy difference, which, as we've seen from the optical clock community, are very useful for precise timing measurements. And so in a sense, we have a hybrid clock atom interferometer where, because of the internal state dynamics, it acts as a clock, but because our atoms are in free fall, not trapped in a lattice, we also have to keep track of the external state separations and make sure that spatially the two arms of the interferometer overlap at the end as well. And just to quickly show a few design models of the experiment is made up of 17 modules. An example module is shown on the right. Each includes magnetic shielding, vacuum pipe, and current carrying wires for generating biased magnetic fields. We'll have 3 strontium atom sources spaced over the baseline with local optical lattices that can launch the atoms, a high-power laser system with stable and agile frequency control, and a well-controlled beam mode and pointing. And the construction and testing of subsystems is currently underway. If you're interested, you can read much more about the details in a recent paper that we put out. And the last thing I want to talk about is the prospects for using MAGIS 100 or other related instruments for observing these sort of effects that Igor talked about yesterday with interfering clocks. Just to quickly recap, the proposal from this original paper on which Igor is a co-author is to probe the influence of general relativistic proper time in matter wave interferometry by carrying out interferometry with clocks, where along each arm of the interferometer, the atoms would be in a superposition, in our case, of the ground and excited states of the clock transition. And then if there's a proper time difference between the interferometer arms, which path information is provided by the clocks, which would lead to visibility decays and revivals. And I should note by several attendees of this conference in Ron Folman's group have demonstrated this sort of clock interferometry where they used a magnetically induced clock rate difference between the paths, which was an important demonstration of this technique. And as Igor talked about yesterday, this sort of dephasing effect could act as a universal decoherence mechanism for large composite objects with many internal degrees of freedom. And so it would be really interesting to be able to observe this effect in the lab. As Igor had mentioned in his talk, for the strontium clock transition, for the visibility to vanish, you need an enclosed space-time area on the order of 10 meters times seconds, which is an extension beyond the current state of the art, but is on the level of what we're aiming for in MAGIS 100. So this may ultimately be possible with MAGIS 100, although I should certainly point out that MAGIS 100 was not originally designed with these experiments in mind, and so a much more detailed feasibility study would have to be done before making any firm claims. But I think since it's such an exciting idea, it's nevertheless worth bringing up the possibility of exploring such measurements. And even if it doesn't work out in MAGIS 100, hopefully in one of the other large-scale atomic fountains around the world, someone could figure out a way of how to implement the measurement. One complication is that in just the standard freely falling Mach-Zehnder interferometer in a uniform gravitational field, there isn't actually a proper time difference between the arms. So we have to come up with an appropriate interferometer sequence that does have a sizable proper time difference. And in a nice paper published in 2020 by Albert Rura, Rura suggested a couple ideas for how one might make this possible. His first idea was to implement a guided interferometer as opposed to a freely falling interferometer, using, for instance, a magic wavelength optical lattice to manipulate both of the internal clock states. He also suggested the possibility of implementing an interferometer in which the clock superposition portion is delayed, so that that then would actually introduce a proper time difference between the clocks in the two arms, and then one could controllably vary the initialization time to observe the effect. And in this paper, he goes into more detail in both of these methods. And so now just to conclude, I've discussed how macroscopically delocalized interferometers can probe gravity in a non-local way, where the wave function doesn't fit anymore into a single inertial frame, and constrains certain models that are gravity related and lead to decoherence. In the MAGIS 100 experiment, we hope to explore even larger delocalizations, and we're interested in thinking further about how we can leverage these larger delocalizations to do things such as implementing this clock interferometry. And so I'll close by acknowledging the people contributing to this work, and also thank you for your attention.
Great, thank you very much. Questions? Sagato.
Oh, I think very, very interesting talk. Okay, so I would like to know a little bit about the time required to get get your sensor. So for example, kind of things we were talking about, this macroscopic interference would require to know any fluctuations of curvature or even acceleration, all the orders quite fast. So what per root hertz, what do you get? Like how much time do you need to say measure some degree of curvature or acceleration?
Oh, you mean like in the measurements, how much average time we needed?
Yeah, exactly.
Yeah. So if we just sort of go, just go back to one of these plots, like for a first example, to measure just whether the proof mass was in or out, then even each shot of this particular rubidium fountain where this was carried out took about 15 to 20 seconds. In the strontium work with MAGIS, the plan is to reduce that cycle time to on the order of a second. But here, each data point was 15 or 20 seconds. And then for this wasn't actually our best statistical data. We had improved that for some other data sets. But here you can sort of see the spread for this particular example data set on sort of the 100 milliradian level. And then we had single shot readout of the phase. So for this big mass, when you moved it in and out, you can tell pretty well even this 1 radian phase shift with just a few shots. Of course, you can average down to get better resolution, and then to get these sort of measurement points to sort of average down to the 100 milliradian or below level, we could take, on the order of clusters of 10 or 20 data points or so. So that was typical for these experiments. Now for the MAGIS experiment, in order to do the kind of dark matter searches or prototype the performance of the instrument as a gravitational wave detector, what our ultimate goal is, and a technical challenge, is to get the apparatus running as continuously as we can. But for these dark matter searches to integrate down, we'd like to be doing that for multiple months, ideally, to get to the level of sensitivity for ultralight dark matter we'd hope to achieve. And similarly for gravitational waves, although we don't expect to see gravitational waves in the 100-meter version, at least unless there's some very surprisingly large signal, in a future full-scale detector that we would hope to build, one would want to observe the sort of sources that one would potentially hope to see in this midband could survive for on the order of several months. And one would hope to observe those as continuously as possible. And one thing that you could gain in addition to this better statistical resolution on the signal is that during that time, if the Earth significantly reorients itself around the sun so that you observe the signal from different angles, there's a potential for then getting angular localization information to do forewarning for electromagnetic telescopes that could be useful for multi-messenger astronomy. So yeah, so we're hoping then ultimately to be taking multiple month scale data.
Okay, thank you.
Yeah, great question.
Over to you, Anupam.
Thanks. Thank you very much. Very nice talk. Enjoyed it. I'm a bit confused. So maybe you can tell me if I understand. So you're saying that you could put some constraint on gravitational decoherence. Am I correct? And if so, what kind of diagram process you were thinking in mind?
Yeah, you mean this sort of local classical channel model?
Exactly. So what kind of what is the process? That's what I wanted to know.
Yeah. So the process in this model is essentially where gravity. What this model proposes is that gravity is essentially a classical entity that. So if you consider the pairwise gravitational interaction between two particles, that information is exchanged not in a quantum way that could produce entanglement, but instead is exchanged classically, which involves in order to determine, it's basically sort of measurement through some ancillae of the positions of the two different particles. And then you say, okay, based on this classical measurement, the position of particle 1 is at x1, the position of particle 2 is at x2. And then based on, Newton's constant and the two masses, I'm going to determine the force to apply on mass 1, and then determine the force to apply on mass 2. And so that's sort of the essence of the method. But because it involves these kind of classical measurements and a classical measurement record of the positions, in order to determine what gravitational forces to apply from one particle onto the other, any position measurement is also classical position measurement is also going to imply some position space decoherence, because in the process of figuring out your position well enough to know the gravitational force that one needs to apply by a feedback on the other object you're interacting with, you're necessarily gaining more information about the position and localization of each individual particle. And so the way this model is framed is that sort of associated position space decoherence is large enough so that before you could actually generate meaningful gravitational entanglement between the two objects, each object will have just been localized. So the decoherence wins out over the entanglement.
I think technically it should be called dephasing rather than decoherence, but maybe we could discuss offline or later on about this.
Yeah, I guess sometimes one can, you can, depending on what one's perspective, one can frame it in different ways. But I think perhaps the reason they called it decoherence is because this localization noise is seen as sort of a stochastic random thing where the information is lost to the environment, so you wouldn't have any revivals. So I think that's why they framed it in that way. But I'd be happy to discuss further offline.
A reason as to why we say it, so called it that.
Okay, one last question to you.
Yeah, Tim, you probably said, you definitely said it, but I didn't get, what's the reason for choosing to work with strontium in the MAGIS experiment? For clock interferometry, I definitely see the gain, but you said that's not what you built it in mind, what you had in mind when you designed the experiment. So what's the gain in going to strontium?
Yeah, excellent question. And so the gain in going with strontium, so we hadn't, so it wasn't to specifically, although it's a fortuitous choice in allowing us to explore the possibility of doing these clock interference methods, that wasn't actually the original motivating reason. The reason to go with strontium was because it has this clock transition, which allows us to have these long-lived superpositions of ground and excited states. And so in contrast to an alkali atom such as rubidium, it allows us to do these kind of single photon atom interferometry where you send one laser pulse across the baseline, it interacts with the atoms at different times, and therefore by sort of measuring the differential times that the different arms of the interferometer spend in the excited state, you get sensitivity to the gravitational wave or dark matter signal. So it's to be able to have the have these sort of hybrid clock/atom interferometers. And I should note that for so strontium directly, that's useful. One useful feature is that it can do both the gravitational waves and the dark matter searches, for at least for these scalar dark matter couplings that would change the clock transition frequency. So it opens up those possibilities. For the gravitational waves, a number of the original proposals were actually based on thinking of alkali atoms such as rubidium. And actually the MIGA experiment in France will indeed use rubidium atom interferometry as for prototype gravitational wave detection. Just one subtlety that one has to keep in mind when thinking of doing for long baseline interferometry 2 photon transitions versus single photon transitions is that because 2 photon transitions, if you sort of look through the trajectories of the photons coming from both directions and the atoms, due to the fact that you need a 3-fold coincidence between the atom, the photon from the right, the photon from the left, or from the top and the bottom, as the case may be, when you're trying to have laser pulses come from both directions to do like a 2-photon Raman or Bragg transition, it turns out that if you have 2 atom interferometers over a baseline, the different atom interferometers will experience light that left the laser at slightly different times, which can open you up to laser phase noise. Whereas the single photon transitions is just one laser pulse coming from the same direction with left the laser at the same time interacting with both atoms. And so that's an advantage for single baseline detection in terms of suppressing laser phase noise, which the strontium clock transition lets you do. But the way MEGA is getting around that laser phase noise issue, which is a perfectly good solution, is to have 2 horizontal baselines that are crossed with each other, in which that cancels out in a common way. And so that's also for these gravitational wave searches a perfectly viable method. And I think it's good that they're exploring a somewhat complementary method to us, since these technologies are all still new. So we should explore the different methods and evaluate the pros and cons experimentally.
Good, thank you.
Okay, I guess we should draw a line under this session now.